All right, guys. Good afternoon, everyone. How are you guys doing? All right. Ready for the weekend?
Yes.
Okay. So today we're going to work on the homework. I wanted to go first to the solution of the experiment that we did in class. So if you remember, you were here on Wednesday. We ran this test in which we loaded this rock sample, Virginia sandstone, to failure to the rock. So that's a video. Okay, and the purpose was to measure the YAM modulus, right? And from here, from the measurements that we did, you were able to make a table of force as a function of displacement. So here at the end of the video, and here probably you can see in your computer much better than what you can see in the projector, but you will see the readings. If you scroll here to the bottom, here you have the table of the values. This one doesn't look very nice. Let me see the next one. Okay, this one is a little bit better, okay? So the first one is the term, second is displacement, third strain, fourth is force, and then you have stress. And if you use those numbers, you will see that at the point in between 50 kilograms and 100 kilograms, the change of stress was 1,000 psi, and the change of strain was 3.75 thousandths. So when you divide 1,000 psi divided 3.75 thousandths, that gives you 266,000 psi. So the solution from Mr. K and Mr. M was correct on Wednesday. So just check your numbers again and make sure you can get to this solution. We're going to do now exactly the same, but with another experiment in which we have a lot more data and with a much fancier device than the one that we use in class. So let me come back here. We are now in homework number 3, and you have to solve problems. Not this one. We'll get back to this later on. I'm sure we're going to have time. But this is the first problem that you have to solve, okay? You have to measure YAM modulus and Poisson's ratio for a shale rock with this dimension and where the data is over here. So let me click, and if you have your computer, you can do this at the same time I do it, okay? So here's the file. We have time, force, and displacement. Okay, so let me show you how we do this, how we solve this problem in Excel. You could also do it in MATLAB or in Python. So what I'm going to do here is, I'm going to click here. There are two ways to do this. Let me use the second one. I'm going to press here raw, and that's going to be the text file. Then you just go to save as. We can find save as. Save as over here, and I'm going to go. I'm going to save this in a new folder. And this is just a data file, okay? So if I go over here, you will see that that's my file. If you double click, your computer may not open it. It depends if you have that extension as a data file, but this is what you see. So you can open this file, as I was saying, with MATLAB or with Python. It's just a text file. Or you could also use Excel. Let me show you how you do it with Excel. Or with any other spreadsheet software. You will go here to data, and from data you will go import from text, and there's going to be a window which should open in a bit. Okay, there's the window, and I'm going to go to the folder where I save the file, and sometimes that file may not appear, okay? Especially when you work in the previous homework, the deviation file, the extension .dev is not going to be recognized by Excel. So what you do here is you put all files. And when you put all files, it's going to try to open anything in it, okay? You're going to see all kind of files in here. So now I'm just going to go here. I'm going to go import. Usually, most of these files, they are delimited. And so I'm going to go just with that delimited next. Automatically here Excel chose a tab spacing in order to recognize that this was data in a tabulated form. Sometimes you could have a semicolon or space to divide the data, but in this case it's tab, okay? So just tab, we'll leave it there, go next, we'll just leave it like that. General format, finish, and there is your data file, okay? So, the same as what we had in the experiment that we did in class, now we have, let's see how many columns of data. We have almost 3,000 data lines as a function of time. Here we have time in seconds, force in pounds, and displacement in inches. Here, I recommend that you insert a few rows on the top, and you're going to have to do exactly the same for the laboratory. And we start filling the properties of our rock. So, can you tell me what was the length of the rock, according to the problem? If I remember correctly, it was 2.01 inches, right? And the diameter was 1 inch. Okay. If we want to compute the stress and we have force, what do we need to compute area, right? So what is going to be the area of this sample? Remember, this is a cylindrical sample. It's going to be equal to pi times square of diameter divided by 4, right? Let me zoom in a little bit more so you can see the formula. So this is going to be the area, and this is going to be in inches squared. And I think now we're ready to start computing what we need. Okay. What is going to be stress? Force divided by area here, right? And if we do it in PSI, this is going to be equal to the force divided by the area. I don't know if you know this cool trick, but you know, I'm now, the cursor is here next to C5. You press F4, it's gonna lock it. Like, you know, like those currency sign. I learned that a few months ago. It was a big breakthrough for me. It saved a lot of time. I didn't know about that. But once you lock it there, then it's gonna always divide by the area, right? So now we have a stress. We copy this, and now we have a stress as a function of time. What else should I compute in order to measure the Young modulus? Which strain? Okay, let's start with the axial strain. Axial strain, what are the units of strain? No units, right? It's unitless. And this is going to be equal to what? Definition of strain was, if you remember, it was displacement, which is going to be in this case x divided by original length, right? And this is going to be the axial strain, and I copy it. And the radial strain now is going to be, also is unitless, is going to be the displacement in direction, in radial direction, divided by, what do you think? The length?
Diameter.
The diameter, right? Divided by the diameter. Okay, so now we have, oh, I forgot something. I forgot to do this, to lock it. So now we have axial stress, axial strain, and radial strain. So with this data now I can insert a plot, scatter plot of stress as a function of strain. Okay. Usually, as we saw in the notes and in class, we plot stress as a function of strain. Okay. So let me fix this right now. So I'm going to move this one over here, this one over there, and that's going to be, let me get rid of the markers. This one out here. Okay, so now we have stress and strain, and these are all your almost 3,000 data points where we have loading, and at this point, this particular experiment, there is what is called an unloading process. So stress goes down with time, and then increases again, decreases, and increases again. Your objective is to calculate what is the Young modulus in this region. Let me check again the problem. It says to calculate the Young modulus in the interval between 0.25 and 0.04%, which is, let me change this to another format. Okay, let me check again. 0.25% to 0.4. So that would be from 2.5 thousands to 4,000. So somewhere around here, you're going to have to choose points in this region and then fit a straight line to that. The slope of that line is going to be the Young modulus. Okay? Let me do something else over here. I'm going to add one more plot that you need for the radial strain, and it's going to be this one. So now we have radial strain and axial stress. What's up, guys?
What's the keys to like just put it, new?
Okay, let me do it again. So, let me see if, okay, I have to go one more step. So what I did was, I just select this. Well, let me check again that it's just one plot. Yeah, it is just one. So you select your plot, you do control copy, so I did control C. I paste the plot in the same plot, so I do control V, and now there are two lines. You can't see it, but there are two lines. So I just choose one of those and move this to radial, and then I get the other one. I could also copy this again, paste it right there, and now I will have 4 lines. So if I were to, for example, now plot that, I will have another one, okay? But let's just leave it like that. Okay, so, but this is now what you need, right? Axial stress in the y-axis, in the x-axis deformation. Positive here is axial deformation, negative is radial deformation. If you plot radial deformation as a function of axial deformation, you're going to get the Poisson ratio. So now I have a plot of here axial deformation and radial deformation negative. The slope of this line in this interval is going to give you the Poisson ratio. All right, so I believe the problem doesn't say anything about unloading, but we're going to measure unloading later on. Usually the curves for loading are less steep than the curves for unloading, which means that rocks tends to be stiffer when you do unloading. And that's related to viscoelasticity, and we're going to talk a little bit more about that. So that's all you have to do in problem number 1, okay? Calculate Young modulus and calculate also Poisson ratio. Yes?
Okay, so Poisson's ratio, the bottom graph, it's kind of curved. Is there going to be like a linear fit through that, or?
Well, notice that this one is also kind of curved too, right?
Right.
So I'm asking you to just find the Young modulus in this linear region. And the Poisson ratio should be also calculated in that same interval. Okay?
Okay.